Hey everybody, my name is Calvin and welcome back to my channel. Today we're going to be talking about one of the most important graph algorithms in computer science called Dijkstra's algorithm. Anytime you hear shortest path in a network with weighted edges, there's a good chance something like Dijkstra's algorithm is running behind the scenes. So think about finding the fastest route in a map app, or routing packets through the internet, choosing the cheapest path through a set of steps or tasks, or even logic inside some games where an agent needs to navigate a world. The core problem here is we have a graph where edges have costs or weights. From one starting node, we want to know the minimum cost to reach every other node. A brute force approach would mean trying every possible path, which, as you can imagine, it will explode combinatorially. The insight here is that we can do much better by being greedy in a smart way. So, starting with the idea. We have a starting node, say some node A, and we want the cheapest cost to every other node. Our high-level strategy is, first, we keep track of the best distance we've found so far to each node in a table or something like that. At the beginning, the start node has distance 0, and everything else is at infinity. We set that to infinity because we don't know how far they are yet. Then, we're going to be repeatedly doing this loop. Look at all nodes we haven't finished yet, pick the one with the smallest tentative distance, then lock that node in as done, and then we try to improve the distance to its neighbors. This works because all weights are non-negative. If a node currently has the smallest distance among all unvisited nodes, there is no way some longer or more roundabout route later will beat it. So once we pick it, we know for sure that distance is final. Let's implement it in Python. First, we import heap q, which gives us the priority queue that we'll need to run our algorithm. Then we're going to be importing NetworkX. We use NetworkX to represent our graph. Each node can be some string or number. Each directed edge has a weight, which we store when we add edges. This is an example on how to build a small directed graph with weights. NetworkX hides the details, but internally it will let us access all the nodes with graph.nodes, the neighbors of a node with graph.neighbors, and then each edge's weight using indexing. Let's look at our implementation now. First, we define the function called Dijkstra, which takes in a graph, our NetworkX graph, and a starting node. Our first step is to initialize all distances to infinity. We create a dictionary called distances, and then every node will get an initial value of infinity, except the starting node, which gets 0, obviously. And this will serve as our table of the best known distances so far. Then we'll create a priority queue. This is a min heap under the hood, which stores the distance and node pairs. We can start by pushing 0 and start, which means the distance to the start is 0. And then we have a variable called set. This keeps a set of nodes that we've already finalized. Once we've decided that a node's distance is final, we're going to be adding it here, and then we'll never process it again. Step 4, we have our main loop. As long as there's something still in the priority queue, we pop the entry with the smallest distance. And this is the greedy aspect of Dijkstra. We always expand the currently closest node. It's possible the same node gets pushed into the queue multiple times with different distances as we discover better paths. If we pop a node and it's already in visited, our set above, that means we've already finalized it with a shorter distance. So that means this entry is stale, and then we'll just skip it. We'll add this node as finalized. So we won't improve its distance anymore. Step 5 right here, we look at every neighbor that we can reach from the current node. For each edge, we read the edge's weight. Then we calculate new dist, which is what would the distance to this neighbor be if we went through the current node. This is the candidate distance for relaxation. Now, our relaxation step is right here. If this new path is better than what we had before, we update the best known distance for that neighbor, and then we'll push the tuple new dist and neighbor into the priority queue so it can be expanded later. Eventually, when the priority queue is empty, then that means we've considered everything as reachable. The distances dictionary will now hold the shortest distances from start to every single node. Then we're simply just going to be returning the distance table. I've implemented a function called Dijkstra with GIF that will, given the same exact inputs plus a GIF name variable and frame duration variable, will generate a GIF of it traversing the NetworkX graph. The logic behind this is exactly the same, so I won't go into it. But this function is how we'll end up generating the GIF we'll look at right now. Let's look at an example, a small named graph. In this graph, we have 5 nodes, A, B, C, D, and E. We're going to be defining the edges like this. A connects to B with a cost of 4. A connects to C with a cost of 1. C connects to B with a cost of 2. B connects to D with a cost 5. C connects to D with a cost 8. D connects to E with a cost 6. Then we run Dijkstra starting from node A, and we'll generate a GIF called example1, which I've inserted below. Initially, distance A is equal to 0, and everyone else is infinity. From A, we're going to be considering nodes B and C. So A to B we know is 4, and then A to C is equal to 1. C is cheaper, so we're going to be expanding C next. From C to B is cost of 2, so A to C to B is equal to 1 plus 2, which is 3, which is better than 4. C to D has a total cost 1 plus 8 is equal to 9. So distance D becomes 9 for now. Next, we expand B, which has distance of 3. From B to D has a cost of 5, so A to C to B to D is equal to 3 plus 5, which is 8, which improves D from 9 to 8. Then we expand D at a distance of 8. From D to E costs 6, so E gets distance 8 plus 6 equal 14. So the final distances we have from A are A to A is trivially 0, A to C is equal to 1, A to B is 3, A to D is 8, and A to E is 14. On screen, you'll see the animation of this process. Watch how the distances table and the frontier of nodes being considered evolves until everything settles. Feel free to slow this animation down on the video playback and observe every single step. Now, let's try a more interesting example with numbered nodes. The graph has more branches and more competing paths, which makes the behavior of Dijkstra a bit more interesting to watch. We define this graph right here, and from node 1, we can go to 2, 3, or 4. From 2, we can go to 5 and 6. From 3, we can go to 6 and 7. From 4, we can go to 7 and 8. Nodes 9 and 10 are the endpoints with multiple possible ways to reach them. Then we run our Dijkstra algorithm. Since there will be a lot of steps to go through even with just a medium-sized graph, I'll just give you the highlights. Node 4 is very cheap from 1, which has a cost of 1, so it'll get expanded early. Node 2 with a cost of 2, and Node 3 with cost 4 will enter the priority queue. As we expand 2, 3, and 4, we're going to be discovering different paths to 6, 7, 8, 9, and 10. Some of those nodes are reachable through multiple routes, so you'll see distances improve over time as Dijkstra finds better alternatives. For example, Node 6 might first be reached from 2, and then considered again from 3. Node 10 can be reached via 7 or via 8, with different total costs. Node 9 is most likely reached through 6 with a relatively low total cost. On screen, the medium-sized GIF is showing the algorithm playing out. The active node gets highlighted, the visited nodes turn green, and the distance table on the right updates as we relax the edges and we improve our paths. Like before, please please slow the video down so you can see it step by step. And that's Dijkstra's algorithm. Thanks for watching, and I'll see you all in the next video. Don't forget to like and subscribe.